students know. So I'm going to introduce Alex, and it's a bit weird for me because I know Alex for such a long time now. I mean, it doesn't seem like a long time, but if I think about this 10 years or as you grow older, you know, even decades seem smaller or something like that. So, and Alex has always been my role model, and I have looked up to him, and I have read so many of his papers. And I think among information theorists in Alex's generation, and maybe a couple of generations before and after, like there has rarely been anyone who has made so many influential contributions that Alex did. So in addition to that, he has won numerous awards, such as the James Macy Award, the NSF Career Award, a Google Research Award, and so on. He is actually the co-director of the other National AI Institute in UT Austin. And as a matter of fact, he is the first non-TILOS speaker in the TILOS seminar series who has agreed to give a talk. And we are really privileged to have Alex over here. The stage is all yours, Alex. Please go ahead.
Thank you. Thank you so much. Thank you for the invitation. And thank you all for attending. I know it's it's NeurIPS deadline, so the fact that you're all here to hear me is a great privilege instead of working on your papers. So I want to first start with thanking and acknowledging my students and my collaborators who are mentioned here. I will be talking about 3 papers primarily. And it was these students who really did most of the inventions and the work that I will be talking about. So we'll be talking about deep generative models here. And I want to just set the stage. These are feed-forward neural networks that take a low-dimensional input vector that we sometimes call Z, or the latent vector, something like 100 dimensions. And they multiply this by some matrices, and they have some ReLU activations, and they have a bunch of layers. They can be convolutional, or sometimes they may have visual transformer layers. But it doesn't matter. It's just a continuous differentiable function from a low-dimensional space to a high-dimensional space. When you put a random input, you get pixels that look like a natural image. And there's a whole big family of these generators. GANs are very famous, generative adversarial networks. This specifies how this neural network was trained through the use of another network, but it doesn't matter for us because somebody trained this already, so we're just going to use it. Then there's another family called autoencoders or variational autoencoders, and we only care about the part that goes from the latent code to the image, then the decoder, that we call the decoder. And then there's score-based generators, which are a little different, but we're using them a lot, and many others. But for this talk for now, we can just think of them as there's a latent space that you may have explicit access like this, or in score-based and diffusion, it's implicit access to this latent space. I will briefly talk about that. And we can just produce samples. And the samples look like the data, but they're different. And it's remarkable that the progress that has been done in the last 5 years in this space is remarkable. And I will show that. So these deep generative models are able to produce or dream, as I say, images. And they have also been trained on other data sets, time series, audio, and all kinds of things, as I will show. And they seem to be remarkably able to learn high-dimensional distributions. We're not sure because we don't know how to check, provably. But every test that we can think of seems to work, as I will show. So there's a website called This Person Does Not Exist. And if you go to that website, every time you reload it, you're going to see an image. And this is, for example, This Person Does Not Exist. It's a very high resolution, impressive image. This was done with a network called StyleGAN2. And it passes what I would call a visual Turing test, which means you cannot tell, I believe, if this image is a real photograph or a fake one. And it's also high resolution now, which is a huge milestone. Other people have trained generators on, for example, aerial photographs. So this aerial photograph does not exist. Or for chemical bonds, this chemical bond does not exist. Then there is this. So this is kind of starting to sound a little silly. I don't know why would anybody, or you may think this is starting to sound silly. Why would anybody train a network that spits out chemical bonds that are just fictional creations or aerial photographs that are just fictional creations? How could that ever be useful? And one of my main points of my talk is that this can be extremely useful. So that's my first big message. By the way, please interrupt me in the chat or by jumping in if you want. It's much more fun to have a conversation if you have any question at any point. Then there's also this family of, these are diffusion models, essentially conditional diffusion models, but there's a conditioning, which means you type some text, like this text, an astronaut riding a horse, it's a typo, in a photorealistic style, and it generates this. And this is not an image that you can get from Google Images. It's remarkable. The way you will know it's coming from this new model called DALL-E 2 is you will find this little logo here in the bottom. So if you've seen this little logo, it's this new model DALL-E 2 that came out a few months ago and has been shocking all of us with what it can do. So this is a conditional generator. Here's another example, a painting of a fox sitting in a field at sunrise in the style of Claude Monet, and it produced this image. And again, here's the secret logo again. And it's amazing, I think. It's remarkable. Like, we have all been experimenting with this, and we have been shocked about how good this is. So I have been sitting in my lab for a while. By the way, these things have been trained with, you know, millions of dollars, resources that are not close to what we can have in a university. Same as TILGAN 2 by NVIDIA, these are trained with very massive compute infrastructure, and access to infrastructure and how AI can stay democratized in universities as opposed to being in 1 or 2 or 3 companies is a huge problem and a huge part also of what I would like to say. So I have been sitting in my lab and I'm able to download these models and run them, but I'm not able to train them. And I'm actually far from being able to train some of them, like DALL-E 2. So I'm asking myself, okay, what can I do with this? So it can generate images of people that don't exist. So what people do is they generate fake pictures and they create fake LinkedIn accounts and so on. And people are doing this, but this is kind of a silly use, right? So I'm saying this is not a real use. So my first message in this talk for everyone is I want you to take away this, forget this, and think of those as incredibly useful, even if you care about maps or molecules or MRI images and so on. And I would like to argue that they are modular and differentiable prior distributions that learn the statistics of your data set. And you can use them to solve the general family of problems called inverse problems. In the inverse problems, you have basically a corrupted image or a noisy image or a noisy sample, and you want to do things like denoise it, compress it, inpainting, which means filling missing data. Colorization means you have an old photograph that's black and white, you want to add color. It's a special case of inpainting. Compressed sensing is a family of problems that many of us have been working for a while that are essentially tomography or linear tomography problems. Source separation problems where you observe the superposition of multiple things and you want to separate them. And the classic example is in audio, you have somebody playing the guitar and also singing. You want to separate the guitar from singing. Magnetic resonance imaging and many, many others, including sparse PCA and so on. So I would like to argue in this talk that if you had a generator for guitar, playing guitar audio, you can use this framework to separate guitar from singing. If you have a generator for MRI, you can use this to accelerate MRI and compress MRI and do all kinds of really cool things with it and so on. So that's kind of the first message. The storyline of my talk will be, I will first tell you about this ICML 2017 paper that's called Compressed Sensing with Generative Models, or CSGM. It's kind of like the first prototype of the framework that we started with. It's an unsupervised way to solve inverse problems, leveraging pre-trained models. So we're not, other people, of course, train their own model to go from measurements back to images, but that's very expensive and very problem specific. Whereas the unsupervised way is leveraging pre-trained models by NVIDIA and so on. So it goes back to this point of not having resources to train massive DALL-E 2 scale generators, but still doing something cool with them. And there's also some interesting theory. If you are coming from the compressed sensing or the theoretical space, we generalized the ideas of restricted isometry properties to images generated by deep generative models. I will talk briefly about that. And if you are interested more, we can talk more in the end, or you can jump in and ask me questions. The theory for this space has also been developing quite a lot. The first question is, solving the inverse problem, as I will explain, requires an optimization problem. And I guess this is an optimization center. So you may like these optimization problems. They are non-convex optimization problems. They are very different from empirical risk minimization, where you're trying to solve for something, but you actually want something else, right? You want something to generalize and so on. So there's no implicit regularization issues. Still, it's a highly non-convex problem, and still, shockingly, they can be solved by gradient descent, but it does need a little bit of tuning to do better in the optimization. So we would love to have more optimization people improving this part. I will explain a little bit. And the other problem I will explain of these compressed sensing with generative models is that these are limited by how good the generative model is. And using GANs like style GAN2, as I say, has certain limitations. And we came up with an idea called intermediate layer optimization, which is another optimization idea essentially in the neural network that solves some of those expressive range problems, as I will explain. So this is the first paper I will talk about. This is the second paper I will talk about. And then I will very briefly talk about our applications to MRI and issues of fairness. I will talk about the paper very briefly on fairness in imaging. All right, so we can start immediately. This is Vijay from Michigan. You may know him. He's my friend. He had invited me to give a talk, same as Arya. I need to update this with Arya, and I'll send it to you. So we got his image from his website. It's a low-resolution image. We removed a big chunk of pixels. And now we're trying to produce an image that has all this missing data. And we will also do high resolution. So we'll do super resolution and Inpainting at the same time. So running the CSGM framework, we got this result. You know, it looks pretty good, as you can see. It knows it has learned all the symmetries of human faces and so on. But if you actually look also more carefully, you realize this is actually a white guy, right? So you can also see the bias, the racial bias that the imaging platform uses. Our algorithm is using a pre-trained generative model called style GAN2. And we thought, and many other people thought, that the problem is in style GAN2. Style GAN2 maybe only knows white people, and it makes everyone white. But with intermediate layer optimization, the new algorithm, if you optimize layers 1 and 2, we get this image. And if you optimize layers 1 and 4, you get this image. And you're still using the pre-trained style GAN2 model. We didn't train a new GAN. We just optimized its internal brain circuits a little bit. And I will talk how we do that, but you can see this is now a pretty good image. You can tell it's Vijay if you know him, and it has a few artifacts here in the ear. I don't know if you can see my pointer, but overall it's solving the intermediate the bias problems to a large extent. So the general framework is X. We have this unknown vector X. These are the pixels of an image. We are not observing them. We are observing a fat matrix, a matrix that the number of rows is smaller than the number of columns. So these are our observations. So this is in the classic simplest case, this is a matrix or a forward operator. So this is a linear inverse problem. And in the simplest case, it is known. There is also interesting work. What do you do when you don't have the forward operator? This is your unknown signal, and these are your known measurements. And you basically have linear equations, maybe plus noise, and you want to reconstruct them. And as you all know, that's impossible to do because the dimension of your measurements is smaller. So there are infinitely many solutions to these linear equations. So what we have all been doing for ill-posed problems is we try to find out of those infinitely many vectors that explain the measurements, we try to find one that's the most natural. So we need a way to define what is natural. And that has been the whole premise of high-dimensional statistics. The classical assumption was that the vector is sparse, or sparse in a basis, or sparse in a learned basis. But now we are going to say that it's not sparse, it is near the range of a pre-trained deep generative model. So this is kind of the general paradigm of what we're doing. So we're going to search in that latent space to find a vector that explains the measurements. You can also think of it in that formulation. You're observing linear projections plus noise. You could be doing explain the measurements plus find a natural image. And the classical things would reward, for example, sparsity of the image, or in a basis. This is Lasso. And Lasso postulates that natural signals are sparse, or sparse in a wavelet basis. And the other general message I want to say is I want you to think of generative models as a new type of sparsity, a new type of model for data. Sparsity itself is a decent model for natural images, but now we have data-driven models, and we want to replace, X is sparse with X is in the range of a deep generative model. Another interesting recent fact is that there was a paper by Eric Price and co-authors that proved that you can create a deep generative model that has all k-sparse vectors in its range and only those, which means this statement is a proper generalization of this statement if you make the correct generative model. This is a more expressive family of natural signals compared to sparse or sparsity in a basis. So that's also an interesting observation. This is the paper. So that we go back to, and I hope I'm making sense. Please ask questions if you want. How do we solve invert problems if we have these pre-trained generators? So, okay, this is our pre-trained generator, like StyleGAN2. NVIDIA trained all these weights inside here. It's very expensive. We're not going to mess with the weights. But if we feed in a random Z, it's going to produce a random face. But I don't want to produce a random face. I want to produce a face that looks like my face, right? So it's very simple. I'm just going to start with a random Z, and I'm going to update Z so that the generated image looks as close as possible to my target image. So I define this loss, which is the generated image minus the target image. I used L2 loss, but you can use a blending of L2 loss and other perceptual losses or fancy blending of functions. Doesn't matter as long as it's differentiable. And you do gradient descent in the latent space, keeping the weights of this network fixed. And shockingly, it works. It doesn't, for some networks, it doesn't work, or sometimes you may need to do multiple restarts or change, parameters or switch to Adam or other optimization methods. But by and large, it works remarkably. So for example, in this example, you get this guy. And this guy kind of looks like me. And but you can probably tell it's, it's not me. You can tell there's some similarity, but here you see the limitations of StyleGAN2. StyleGAN2 can produce very nice images, but it's not ever perfectly able to match our faces, or at least my face. Also, the fact that I have glasses here makes it harder for this network. And the fact that I have a beard makes it hard. So the general idea, the first idea was, let's just guide. We're not just asking the generator to dream of random images. We are guiding the input through optimization so that the dreamed image matches some desired specifications. As long as it's a differentiable set of specifications, you can do gradient descent because you're backpropagating through this network, and you can make it produce the images you want or do something close. This was, of course, proposed by us in 2017, but also proposed by many other people in slight variations because it's a very, very natural thing to do, right? But there's a little bit more. Now, let's say you have an inpainting problem. You're going to search in the latent space to produce an image that agrees with the observations only in the parts where you have observations, right? If you have missing data, you have to remove those from the loss. So the cleanest way to do this, as we proposed, is A is the forward operator. And you say the measurement, you want an image so that after it has been measured, it agrees with the observed measurements you have. And because A is a matrix, that's still a differentiable function of Z, so you can still do gradient descent in Z. And we got this result. This is from our CSGM paper, which is pretty good. It's not perfect, but it's pretty good. Again, you can see the mouth doesn't perfectly match because the generator is not able to produce perfectly all kinds of human mouths. And as generators are getting better, if you replace this box with a better box, then this algorithm will do better, unless the optimization starts creating problems for you. Same algorithm you can do for deblurring or super resolution. Here, Blurring is a
Alex,
convolution with a Gaussian kernel. So you can just say, I'm looking for a generated image so that after it has been blurred, it matches my blurred observations and you get this image. So these are all the results we were getting in 2017, just leveraging pre-trained DC GAN. This is the general algorithm that's called CSGM, which is simply do gradient descent in the latent space to satisfy the measurements. And you do get useful gradients because of backpropagation. So I don't know if this makes sense or anybody has any questions on this step.
So you do have this A operator. I'm just trying to understand the meaning of this. So you, so why do you have to do compressed sensing here? Can you just not get rid of that part and just say, I do have this observation and I'm going to use this, I'm going to use gradient descent through this pre-trained model to generate it. I mean, why do you need this A?
It depends on what problem you're solving. If the dimensions, if you're observing a noisy in this problem, this is Y. And the dimension of Y is the same as the dimension of G of Z, right? So then you can literally say G of Z minus Y L to north, because the dimension of this vector and this vector is the same. This is called projection, projecting an image in the range of the generator. You can also think of it as denoising. But in some problems like this one, your Y now is not a fully dimensional image because these pixels are not black, they're actually missing. So the dimension of Y is actually a shorter vector. So you have a shorter vector and you have now your big image that you're going to generate. This is your G of Z. So you need to project in the observation space. So this is what A is doing. A here is just a subset of the identity matrix that has a row for every observed pixel. So you can write in painting in this mathematical form. So A is basically representing what problem you have. In this problem, you do have a full image, but the image you have is blurred. So you could run minimize G of Z minus X1, but it's like you're asking your model to make a blurry image. And the network should not know how to make blurry images. So instead you say, make an image. So now A is a blurring operator. It is, you can write a convolution with a Gaussian kernel as a matrix, a Toeplitz matrix that's multiplying X. So that's what A is here. So A in the general framework, thank you for the question, is representing what inverse problem you want to solve. And every problem that can be written in this way is called a linear inverse problem. But you also quickly realize that you don't need this to be a matrix. It can even be a neural network, or in phase retrieval, it's a nonlinear operator that is, dropping the signs. Or you can do Fourier transform, for example, and drop the phase of the Fourier, and that would be a nonlinear A. And people have still applied this framework for nonlinear operators, as long as it's differentiable.
Right. So this can, in particular, be some sort of quantization.
That's right. In fact, also we and other people have worked a little bit on using this framework for quantization. Yeah, if you observe quantization or even projection and quantization and all these problems, you can run this. Now, I don't know if it will work. If it's quantization, actually, there's an issue. It may not be differentiable straight up, so you may need to optimize it differently. But absolutely, yes, it can be any operator that corrupts your image and gives you the measurements.
I see.
Yeah, but
Professor.
Yes.
So I had a question in the super resolution scheme. Like maybe if you're completing something that some sentence, you can complete that, and I can ask it after that.
Sorry.
Can I ask the question right now?
Yes, of course.
Yes.
Okay.
Yes, please.
So in the super resolution image, your target is, I guess, yeah. So it seems like the algorithm may create a different kind of artifacts. So in that sense, how do you check whether the image has actually improved the resolution? So for example, if it were a problem of estimating the frequencies in a signal, so it could create frequencies in some random places. So how do we check whether it has actually improved the resolution?
Yeah, great question. So the way we check is we take a lot of real images that are not blurred. We blur them ourselves, so we have the ground truth. We run the reconstruction algorithm and we compare it to other deblurring algorithms, and we look at the mean squared error of the reconstructed images that our algorithm gets compared to the reconstruction, compared to the ground truth. So we can also not use mean squared error, but use other metrics like LPIPS or SSIM and so on. But in all the experiments, I will be showing plots like this, where what you're putting on this axis is the real reconstruction error. So this is the error of the ground truth image that the algorithm obviously doesn't know, minus the image it produces. And we are comparing. So here in this example, we are plotting two standard Lasso variations, Lasso in the DCT basis and Lasso in the wavelet basis. This is the performance. And on this axis, we have the number of measurements. So in this problem, it's like a Gaussian projection. So it's compressed sensing problem. You're observing random linear projections of your image. You're trying to reconstruct your image. Your image is about 13K dimensional. So if you're observing only 100, so there's 13,000 pixels you're missing, so to speak. And if you're observing, that's the main point. If you're observing only 100 or 200 measurements, there is not much hope of reconstructing it very well. But this is what the deep learning algorithms were able to do with 100 or 200 measurements compared to the Lasso methods. So the thing we said here, if you're familiar with the Lasso methods, we said that we matched the performance of Lasso in 1,000 measurements with 100. So it was about 10x fewer measurements in this setting, which was shocking to us and everybody else. And I will show you more examples of this. But the direct answer to your question is, I have the ground truth and I'm computing compared to the ground truth. That's how I know that I'm not messing up. And I will talk more about it in a few minutes.
Thank you.
Thank you. Thank you. Yes, and there's another question.
Yeah, there is another one. Kunal.
Hey, yeah, so thanks again for the talk. So one question I had is that, I mean, of course, like the size of the data set on which you have, trained these generative models, like how does that influence, whether you're able to find a solution or not? For example, I don't know what kind of ethnicities, since you're looking at just faces, the ethnicities, or maybe, whether they're wearing, say, glasses or stuff like that. I mean, I can imagine like the more homogeneous a data set looks like, it might be easier to optimize. If it's more heterogeneous, then it might be difficult. So can you comment on that?
Absolutely. So yes, you're absolutely correct. And this is very much reflected in this example. And this is also why people were not able to do this very well for a while before the ILO idea. So the network, just one remark, I did not train this generator. NVIDIA trained this generator. It's very expensive to train this generator. Okay, so it's not easy to train. You can do it if you have a lot of GPU hours, but I don't want to play that game, and it's impossible for a university to play that game. So yes, this generator, the image it produced to match my image, as you can see, indeed has a lot of problems. You may be able to tell it's influenced by my picture, but it's certainly not good. And you're absolutely right. If you try it on young, good-looking people, without young white good-looking people without glasses and beards, it does very well because it was trained on celebrities, right? Who tend to be good-looking young white people for the most part. So yes, of course it is. The generative model has its own training set. Of course, if somebody like NVIDIA trains a better one, that's better for all of us. But I will try to find a way. I will tell you how ILO is a way to still take StyleGAN 2 and be able to reconstruct our faces pretty well. That's what I showed with VGA also. So there's an algorithmic innovation, but you're absolutely right. We're very much constrained by these models, but gladly the progress in these models in the last 5 years has been mind-boggling. So we are benefiting from that. Very good question.
I mean, like, have you, ever experimented, like, for example, if you somehow are able to get your hands on a model trainer on different, sets of data sets, right? One is just, say white male, one is like, okay, white male, female, and stuff like that. And did you see any systematic difficulty or ease in terms of the optimization, like, or have you not found that experiment?
Yeah, absolutely. So it's not so much, there are two issues going on, the optimization and the bias. So it may produce images like this one, which have a somewhat small mean squared error, but then may, I mean, I'm going to get into this, but are you familiar with what's called the white Obama fiasco in this space for this problem? Okay, so yeah, so then hold your thoughts, because there's a lot of things coming from this. But yeah, basically it's similar to the VJ bias issue, right? So it produced this image, which is very close in mean squared error to the observations, but it's actually a white guy. So so it's actually quite hard. So I will argue how you can address this problem to some extent by intermediate layer optimization or posterior sampling. These are the two ideas that we have. Of course, if you also make a better generator, that's even better. It will reduce bias even more. But that's not something that a research lab can easily do. Also, we don't have data. We don't have 20,000 images of humans and so on. But absolutely, all these points you say are spot on.
Right. Just one last comment. So since I think this paper is back from 2017, right? I'm just curious. I mean, GANs have become larger and much better, more recently. Like, do you have any slides for that, or
Yeah,
if, for example,
this image
the
is not
one.
from 20. Great. This image is not from 2017. This is StyleGAN 2, which came out. I don't know, maybe 19. This image is from DC GAN. So DC GAN produces 64 by 64. This is just 64 by 64 pixels.
Right.
Whereas this image is 1024 by 1024.
And so did you observe any systematic, ease or like the way you optimize when you're dealing with images of different resolutions?
this model, absolutely. StyleGAN 2 is much harder to optimize. It's a much deeper network. So optimizing in the latent space for StyleGAN 2 is a much harder optimization problem. And we needed to do more and more tricks in the optimization to be able to get even to this result. So the depth of the model makes the optimization harder.
I see.
And that is also a key. That's also a key issue. Yes.
Okay. Sorry, and not to take more time. Like, do you have any pointers? Like, for example.
I will have pointers. I will have pointers at the end. But thank you for asking the questions. I think it's good for everyone to get into the points that I'm making. So I'll continue, and then you'll see some of this more. So this is the general idea. Do gradient descent in the latent space to satisfy the measurements. And we obtain useful gradients because we can backprop through the generator, and we can hopefully backprop through the forward operator. There are other methods for solving inverse problems that are not using a pre-trained generator. These are supervised inverse problem solutions that simply train neural networks to go from measurements to reconstructions. And they work very well, but they're very specialized. You have to train a neural network for a specific forward operator. Whereas I trained a neural, I didn't even train one. Like NVIDIA trained one, and I'm using it for any forward operator. So the benefit of unsupervised methods is you don't need to train generators yourself. You just need a generator for your data, and you can solve inverse problems out of the box through optimization. So it's optimization fighting pre-trained neural networks, so to speak. And we have a survey of that. If you're interested, this is a general survey of different families of techniques for inverse problems. But we're sticking to this CSGM style of techniques that are basically optimization techniques. And as I said, in our 2017 paper, we showed very big gaps from sparsity-based methods. But there's also this issue that in high measurement regime, CSGM actually doesn't perform better anymore. It has kind of saturated, whereas sparsity-based methods are outperforming it. And the reason is, this is now the representation capability of your generator. At this point, if you have more than 500 measurements, you need to throw away this generator and get a bigger one, a more expressive one that can benefit from more projections or more observations. So I'll briefly tell you about the theory results. and we can dive more in the questions if you want. So if you're observing, if you have a linear inverse problem, and I'm going to in my proof, I'm going to assume A is Gaussian and independent. You would like to solve this problem, and this problem involves finding the latency that explains the measurements. As we said, this is a non-convex problem, and provably we have proven in another paper it's NP hard. But still, if you could find this, and if your measurement matrix is created randomly and independently, Gaussian, then if your number of measurements is k, this is the latent dimension of the generator, times the depth, times logarithm of the ambient dimension, then your reconstruction that you are going to get by solving this optimization problem, this is the reconstruction you get, this is the error you get, is a constant times the best possible image that your generator can produce. So the good thing about this is this doesn't have A. There's no A in this expression. So this is basically measuring how good your generator is. So it's basically saying if you can solve this optimization problem in the latent space, the reconstruction you get is going to be close to the best reconstruction this generator can do if the number of measurements scales linearly in the latent dimension, linearly in the depth, but only logarithmically in the pixel space. And if you're familiar with compressed sensing results, it's kind of along the same style. And then there's another result that's slightly different. It says, I don't need my generator to be just matrices and ReLUs. It can be any function that has a bounded Lipschitz constant. And then the number of measurements is linear in the latent dimension and logarithmic in the Lipschitz constant. This is how many measurements you need to reconstruct with this type of guarantee by solving the latent space optimization problem. And if you are familiar with restricted isometry property in the classical compressed sensing theory, it's a property of these measurement matrices. Basically, you want all sparse vectors to be far from the null space. And to prove this theorem, we defined a set restricted eigenvalue condition that asks the differences between pairs of generated images to be far from the null space. But these are generated images now. These are not just sparse images. And the key lemma we proved is that random matrices Gaussian with k log L measurements will satisfy this Schreck condition with high probability. And if you are even more in the theory, the way this is done is by trying to create an epsilon net in the generator space. So this is a manifold of natural images in the ambient space. It's a very strange manifold. I'm trying to create an epsilon net for it. And I'm trying to see how many points I need to create that epsilon net. This is called the metric entropy of the generator range. And the way we do that is we say we're going to make an epsilon net in the latent space, which is a good sphere. But this is distorted now by the mapping G, which has a Lipschitz constant L. So using L is a bound on saying, if I want a good epsilon net here, how dense should my epsilon net be here so that even after the distortion, it still has a good coverage in the image space. And that's how you get the log L here. The proof is standard proof of RIP properties with this extra twist of using the Lipschitz constant to get the distortion. So I can dive more into this if people are interested in the theory. But it's kind of normal compressed sensing technology applied in this manifold. And the second problem that may be of interest to people who do optimization is, okay, to do this theorem, you said you're able to actually optimize this crazy function. But this is, as I said, provably NP hard if there is more than 3 layers in the generator. So how to do it efficiently? There was this beautiful sequence of works starting with Paul Hunt and Voroninsky in 2018, where he proved that if this generator has random and independent weights, if you do gradient descent, with high probability, you are actually will be able to solve this problem, which is non-convex, which is shocking. But it's for a random generator. And the extra condition they needed was, the first layer has size k, and they needed the second layer to be at least k log k, and the next layer to be k log k square, and so on. So they needed this expanding property of the generator, that every layer is significantly bigger compared to the previous one. So then they showed the gradient descent indeed with high probability solves these non-convex problems for random weights and this expansion, which was a very, very interesting result. If you're a coding theorist, and I guess Arya, I know Arya is, I don't know if you're still training coding theorists, the proof reminds me a little bit of density evolution. But I still haven't found an explicit sort of connection.
So this works for any activation function. I mean, the non-linearity doesn't matter.
No, ReLU only.
Only ReLU.
ReLU only, but that's not a problem because we have ReLUs in real life too.
Right.
So that's not the problem. The problem is this log factor every time.
Mm-hmm.
Because the reason this is a problem, or we argued it's a limitation, is in this paper, we showed that we can do it with a constant factor rather than a log k factor by inverting, as we say, one layer at a time. So if you're observing the pixels here and you're trying to reconstruct this layer, we can, this is just linear equations in the realizable case. These are linear equations with ReLU. So they are like ReLU linear equations. But if there is an expansion factor of more than half, you get enough linear equations to solve this problem and invert one layer at a time.
I see.
So we were able to do this.
It boils down to this single index model where your nonlinearity is ReLU. So y equals to ReLU of ax. So
that's right.
If you can do that, then you can go layer by.
That's right. I call this ReLU regression, but absolutely correct. Yes. So. But this was with this different algorithm that solves one layer at a time. And then Daskalakis, Dhruv, and Zabetakis proved that constant expansion, so now you can read the title, constant expansion, which means not log k, but constant, suffices for compressed sensing with generative priors. So they showed gradient descent will solve this problem with constant expansion. So they changed this into some constant that I don't know. So that's kind of the state of the art of this family of papers, where they analyze random optimization problems that come from this, and they prove that with high probability gradient descent we'll be able to solve it. This is I think the state of the art paper from NeurIPS 2020. Unfortunately, real generators don't keep expanding. They start expanding, but at some point there is usually a contraction layer that produces the last vector. So that's where our theory separates from practice. The ReLU activations are actually, like all the networks I'm showing you, all the images I'm showing you have ReLU activation. So that's not a big problem.
I see.
So yeah, that's kind of the state of the optimization, and we can only do it for random G. Now, if we could do it for, and then there was another paper that said we're going to do this optimization method called surfing. By Langford, that said we're going to start from a random network and we're going to update this z hat by getting closer to a given network. So it's a sequence of optimization problems that starts from random weights and gets you to some other weights. But I don't fully understand all the details of that work, but I found it a very interesting variation where they can actually prove something for non-random generator weights. So that's the other paper that I have seen in this space.
Right. And I think the main limitation would be that G is all this theory is for random G, whereas these are very these pre-trained networks are very specific, right? So that's.
But absolutely, of course, that initially sounds ridiculous until you see how beautiful the math is, and then the other argument is. That if the network is severely over-parameterized and you are actually doing not so many gradient descent steps when you're training it, you're not that far from a random network, actually. And there have been some theories about quantifying that. So it's not as absurd as it initially sounds to represent these networks with random weights, I think. I mean, if you can prove something interesting about it.
Right.
So this is kind of the theory. This is my understanding of the theory. Landscape.
No, but very interesting, I think.
There's a lot of interesting questions on this, and I prefer to have a conversation and not cover all my topics rather than blasting through all my
I
topics.
will just not hold you. Like, please go ahead with the talk. I think.
Yeah, it's fine. It's fine. It's more fun to have the conversation. I'll talk about another issue. Some generators. So as I said, some generators are functions that go from a low dimensional latent to a high dimensional pixel space. And as we said, if you have a bounded Lipschitz constant, and you will always have a bounded Lipschitz constant if you're multiplying by matrices and doing ReLU, the trivial bound is the largest singular value, the product of the largest singular value, or something like that. And because we have logarithmic dependency on the Lipschitz constant in our measurements, it's not a big deal to get a very loose bound on the Lipschitz constant. But these generators, as I'm saying here, are producing actually manifolds. Their range is a set that has count of dimension at most k in Rn. So it's indeed a lower dimensional subspace of Rn. And in this setting, the CSGM theory that I briefly spoke about says the number of measurements is k log L. K is the dimension of the latent, L is the Lipschitz constant, which is great. This is, by the way, for Gaussian. You can also choose to analyze other random matrix families. The same way that people in compressed sensing said, I'm going to prove this family of matrices have RIP. The same problems are open for CSGM, where you would need to prove this SREC property rather than the RIP property. But some modern diffusion models, some model generators like invertible flows, score-based models, or diffusion models, like DALI2, for example, which produced these amazing results, are not GANs. They are what's called diffusion models or score-based models. And these models do not have a low dimensional latent space. They are not optimizing, they don't go from a Z to a G of Z. They actually only give you access to a gradient of the log likelihood directly in the pixel space. So what we know about them is that they are fully dimensional distributions. So how could you hope to get a meaningful sample complexity bound when you have distributions fully supported in Rn? It seems that there's nothing you can do. So we define this concept that's called the approximate metric entropy. And the approximate metric entropy is the following concept. If you have a distribution in a high dimensional space, let's call it P, like, for example, the distribution of human faces or MRI images, and you give me two parameters, sigma and delta, the approximate metric entropy of this distribution is the smallest number so that I can cover this distribution with balls of radius sigma, but I don't need to cover all the mass because it's impossible to cover all the mass with finite balls because it's a distribution in Rn. I just need to cover most of the mass, okay? So it's like other concepts of metric entropy, but the approximate is the key, and I'm covering 1 minus delta fraction of the probability. So the statement is, just to be clear, for any distribution in Rn with parameters, you give me some parameters sigma and delta, I define this covering number, which is the number of balls needed to cover this distribution, but I don't need to cover all the mass. I need to cover 1 minus delta fraction of the mass. So I'm putting balls and I'm covering most of the mass of the distribution. And our result is that if you have an inverse problem now where you want to reconstruct an image sampled from this distribution, if you can do posterior sampling, which means you're sampling from X star conditioned on your measurements, then the number of measurements you need is constant times the log covering number. So this is the approximate metric entropy. So this is similar to many other results in information theory and compressed sensing, but we think it's new, and we think it's particular to this type of problem because you're not trying to fully cover the distribution, you're trying to cover a big fraction of it, and that will give you this guarantee with this much probability. So the reconstruction you get from posterior sampling minus the true unknown sample is bounded by a constant times sigma with probability that depends on delta. So this is a very general result that we established in this paper, which is deviating a little bit from the CSGM framework, because in the CSGM framework, you're trying to optimize in the latent space, but now you're trying to actually sample from the posterior. So I want to wrap things up quickly, but I'll show you two results that on the fairness issue. I guess I'm kind of running out of time, but the ILO issue, the ILO optimization, I realize now I'm out of time. But the ILO idea was, instead of optimizing, so let me just show you what ILO is very quickly. ILO says, instead of optimizing in the latent space, you're going to go and optimize in some intermediate layer. So you first optimize in the latent space, and you use this as a hot starting point, as a starting condition, and then you start optimizing in an internal layer of the style GAN2 architecture. So after you run the normal CSGM, you get this guy, and then you optimize in the second layer, and you're optimizing only inside the generator, and you get this image. And what I want you to look at is that this image is not my picture. It is actually generated from style GAN2 with an internal optimization in its own latent space. Not in its own latent, in its own internal space. So we're able to get results like this. But if you go too deeply inside the latent space and you optimize in some other layer, you can get results like this, which are now Picasso type of interpretations of my face, because the network now is too expressive. You have made the network too expressive. The deeper you go in optimizing this neural network, the more general images it can produce, and that ends up departing from the space of images. I want to show you some results on Inpainting that we found quite shocking. This is an image. This is what we observe. This is the ground truth. This is Stefano Hermon, who's my friend from Stanford, and he gave me permission to experiment. From these observations, if you run the previous state-of-the-art CSGM type of algorithm, you get this result, which is a nice image, but it's not Stefano. Whereas if you do intermediate layer optimization, you get this image. And I think if you know Stefano, you could possibly guess this is an image of Stefano. But I don't think you would be able to guess from this image what it is. In this experiment, you're observing 1% of the pixels. So I don't know if you can see, there's a dust of pixels here. And from this dust of pixels, we're able to reconstruct this image. This is the previous state of the art, and this is the ground truth. And when my students gave this, I said, I don't believe you. I think you have a bug. There's no chance you're reconstructing this person from this dust of pixels. But now we think that from 1% of the pixels, using style GAN2, with intermediate layer optimization, you're able to reconstruct faces, which was shocking to me. On the blurring, and going back to the problems that people mentioned, these are three blurry images. This is what you observe. This is the blurring and super resolution. This is the previous state of the art, the second column, and this is the White Obama fiasco. So the previous state of the art method started with this image of Obama and produced this guy. And if you search White Obama AI, you will find a lot of articles written about the White Obama reconstruction. And you can see how it's an image that kind of looks like this image, but it's a white person. And this is using style GAN2. Our method is ILO, still using style GAN2. So this is still using the same generative model, but as you can see, we're getting a much better reconstruction. And this, of course, is the ground truth. And you can see the same bias effects happening here. And okay, here it's not as bad, but I don't think you would know who this person is from this image. So the fairness issues are quite huge. This started on Twitter, where somebody made a super resolution image, super resolution pipeline, where people were uploading this and they were getting this and they were saying amazing. But then somebody uploaded this and they got the White Obama fiasco. And you can see here this became viral on Twitter, and that's how this whole thing started. So our solution, we have two ideas to propose. Again, in this experiment, you can see these are the original images in the top row. These are the measurements that our algorithm is observing. This is the previous state of the art. And you can see it's terrible, okay? It's not that the White Obama was a cherry-picked case. It's literally has all kinds of biases across the board. Like it's doing this, it's doing this, it's doing this, and it's doing this. And these are all failure cases. So there's two innovations. Doing ILO, intermediate layer optimization, and instead of doing gradient descent, doing noisy gradient descent. So every time you update your Z so that G of Z matches the measurements, add a little bit of noise. This is called Langevin dynamics. And you can prove that instead of trying to find the mode of the distribution, the most likely image that produced these measurements, this is essentially trying to sample from the posterior. Okay, so our main messages are, instead of trying to do gradient descent, try to do Langevin dynamics. If you have a score-based model, it's even better because the score-based model gives you the score. So naturally it does Langevin dynamics. And don't try to find the map solution. Try to sample of P of X conditioned on Y through Langevin dynamics, which is noisy gradient descent. And we have a whole paper where we prove certain nice fairness properties of posterior sampling that I could get into if people have questions. But the main point is, already visually, you can see here that posterior sampling is much better compared to trying to find the mode of this distribution. And also ILO is also much better. But yeah, I guess I will wrap up in a minute and take questions then. So, by the way, just very quickly, we applied the same techniques to MRI. We have a NeurIPS paper where we trained a generative model, a score-based generative model on MR images, and we get pretty good results and a lot of robustness. So just main points. CSGM solves inverse problems very well, but is limited by the expressive range of the generator, as many of you pointed out. ILO expands the range by optimizing intermediate layers, and we can get sample complexity bounds by assuming a solution to this optimization problem. Score-based models are usually more flexible, and you should be able to try from the posterior using Langevin dynamics. And we have some theory for that on the number of measurements, as I briefly talked about. Posterior samplings also gives you better fairness properties, and we have a whole paper on that. We can talk a little bit about, but still, there's many things to think about in fairness for imaging. And optimization in the latent space can be guided by all kinds of differentiable cost functions that can be added in a plug-and-play fashion, which is a very nice framework for solving all kinds of problems. So I'll stop here. Thank you very much, and take questions.
Thank you very much, Alex. I mean, this was a great talk, and I have a couple more questions. It's great that despite of so many, questions, you still managed to finish it right on time.
Well, I skipped half of the talk.
Well, we have to re-invite you to listen to that other half.
Yeah.
But I have some question, but I see some raised hand as well. So I will let the others ask the question. Kunal, I see, can you go first?
Sure, thank you. Okay, so I think my question is about the last slide that you talked about the fairness. So, yeah. I mean, I don't quite understand, like, so if my understanding is correct.
Yeah, I'm getting there.
Yeah, okay, sure. I mean, so maybe I can say my question in the meanwhile. So my understanding is that the baseline that you show here, right, or the prior state of the art, all of these methods are trained on the same data set, right? Is that correct?
Yeah.
Okay, so I mean, so generally, when it comes to fairness in AI, like people, they comment that it's a matter of data set.
Yeah, great.
But somehow
I got you. Hold that thought. So is it a data set problem or an algorithm problem? Is that the question?
Exactly. I mean, looking at your slide and the fact that you're using the same data set, it seems that it's it's a matter of algorithm, but that doesn't make any sense because whether someone is white or male versus female seems to be more of a human concept, not a math concept, right?
No, well, yeah, so we talk about that extensively, but I'll tell you the punchline, or at least one punchline. Is it a training data set problem or an algorithm problem? So as you said, indeed, when these results came out on Twitter, many people came out and said, including Jan LeCun, saying it's a data set problem. Just train a style GAN 2 with a better representation and it will all be done. I would like to argue, and we show this in our paper, that this is not the case. The algorithm matters tremendously, and I will explain this with a 2-minute probability exercise. So here's my probability exercise. Thank you for asking. Let's talk about map inference, okay? Map inference in a simple toy problem. I'm going to flip a coin 10 times, and the coin is biased. It comes heads with probability 0.6. So I have a sequence here that's like 60% heads, right? Heads, tails, heads, tails, heads. And I'm asking you to guess what you have to guess a sequence to maximize the probability you are correct, okay? Are you going to guess a sequence that has 60% heads and 40% tails? Or what's the sequence you are going to guess if you're...
Yeah, I mean, I can understand, like you may be tempted to do that, but I mean, randomness is truly random, right? So you cannot say that it's always 60%.
Well,
right?
randomness, no, but you see, the algorithm is observing some measurements, and the measurements are telling the algorithm every coin is 60% to be heads. Now you have to produce a sequence, like an image. So the algorithm is not going to produce something like this. The algorithm is going to produce this, because that is the maximum likelihood estimation for this problem, right? And what I'm telling you is that if you run map inference, which corresponds to gradient descent, which corresponds to CSGM, you are going to take a little bit of bias and amplify it, because the algorithm is obsessed with finding the image which has the maximum probability of being correct. So if you see a blurry image and it is 51% a white person, you're always going to produce a white person, because you want to maximize the chance to win. That's what maximum likelihood is, right? So what we're saying is, don't do maximum likelihood, sample from the posterior instead. So if you're sampling from the posterior, for every coin, you're going to flip your own coin and make it heads or tails with 60%. So that's kind of the simplest way I can explain the message, that the algorithm should not be map, the algorithm should be posterior sampling. And we have, as I said, a whole paper where we get much more into this. But this, I think, is the cleanest 5-minute message, that the algorithm for imaging matters. It amplifies biases that are in the data set. And the simplest way you can fix it, or the first step, is don't do map, do posterior sampling. There's more things you can do, of course, but that's the simplest thing.
I see. I think that's a very interesting take on the problem. Yeah, I feel
perspective, but like so when you move from map to posterior sampling, maybe you're increasing the fairness, but are you giving up accuracy in some way?
Well, yeah, that's also a debate. Yeah, so it depends how you measure. Yeah, usually yes. Usually, if you care, I mean, you have to define it correctly, but yes, usually you are. Yes, if you care about, I mean, as you know, what is minimizing mean squared error? Let's define accuracy as a mean squared error. You should be not sampling from the posterior, but do the conditional expectations. So sample from the posterior 1,000 times and average those images. That is going provably. So you see, and you know, you're probably teaching these classes, right? And that's why we need to stick to our fundamentals here, right? So there is maximum likelihood, conditional expectation, and sampling from the posterior. These are different things. And, you know, many people who are just hacking away in TensorFlow and Torch all day don't even know the difference. But in practice, they are different things. And they're going, if you care about mean squared error, you need to do conditional expectation. Sample from the posterior 1,000 times, get 1,000 images, average them out. That's going to minimize your expected squared loss. That's if that's your accuracy metric. But I don't think your accuracy metric should be that. I think you should care about fairness explicitly, actually.
One other question regarding the Langevin, you said that it is, because it is doing this posterior sampling, that's why. But is there like an optimization perspective to it when you are changing your algorithm to Langevin dynamics? Maybe you are doing a better optimization, or to like your algorithm.
Yeah. So I showed two different results, and you're right. So I showed also intermediate layer optimization also mitigates the bias a lot, because it just makes the generator much more expressive. That's just gradient descent. But in this experiment, so in this experiment, it was just ILO. So just better optimization in the intermediate layer fixes the biases because of a better generator. But in this experiment and in this paper, we argue don't do gradient descent, do noisy gradient descent. So the practical version of what I'm saying is, instead of minimizing G of Z times A minus Y, do that plus noise in each step of your gradient descent. And that's, as I said, is essentially Langevin dynamics. So Langevin dynamics is essentially replacing sampling, is doing sampling as opposed to trying to find a map. Right. And it also gives you sample diversity, right? Every time you run the reconstruction, that's another benefit. Every time you run the reconstruction from this, if you run Langevin dynamics, you're going to get a different image. Slightly different. And then you can average them, or you can even get per pixel uncertainty quantifications, because you can get 100 images and say, oh, that's how much I trust each pixel. The problem is it's slower, of course. It may take you 10 minutes. It takes about a minute with this method to get a reconstruction from these measurements. So if you want to get 100 or 1,000, you have to wait, 1,000 minutes or 100 minutes. So it's not very practical right now.
Yeah, I mean, this is actually cool because fairness is one issue, but and I agree, it's a very major issue. But even if you take out fairness, even the reconstruction itself seems much better, right? So
yeah, in this case, yes, and that's because StyleGAN 2 has a lot of limitations. The other thing to know is mean squared error is a very misleading metric sometimes. So it could be matching the background better or something. I mean, in this case, you're right, but mean squared error can be very misleading. And there's another aspect of bias that is also a major in this. So you see here, if you trained, I was joking about it in this tweet, but it's true that we trained the generative model for MRI, and it may look at one of your kidneys and it may imagine that it's a cat. So that's kind of funny, but if it has only been trained on one family of tumors, and then it reconstructs a tumor of a specific patient using bias from other tumors it has been trained on, that's a huge problem. So bias in imaging is a huge problem beyond the fairness issue if, for example, you're doing it in medical imaging. So that's another aspect that we care a lot about.
Okay, yeah. Well, this has been very informative, Alex. I learned so much. Yeah. Yeah, thanks a lot for coming, and hopefully I will see you in person sometime soon.
Yeah, this is a list of the papers that I spoke about, and if anybody's interested, follow up by email. I'll be glad to chat and help in any way. So thank you very much for having me. Thanks for staying along.
Thank you. So yeah, let's thank Alex again, and bye-bye.